Hello, so welcome everyone to our new series of sustainability seminars this semester. We are organizing these seminars to raise the awareness of sustainability. It's organized by Students for Sustainability, and we are doing it with the support of Office of Sustainability and Graduate Affairs. Our seminar today is addressing the urban water demands in a sustainable way by Professor Peiying Hong. And this seminar will focus on the major challenges for the water resources, both in quantity and in quality, due to climate change and rapid urbanization. As water demands rise, we need large volumes of fresh water that will put more pressure on already water-scarce regions. Professor Peiying Hong will explore these pressing issues and offer new insights on how we can meet the water needs in a more sustainable way. Professor Peiying Hong obtained her PhD degree in environmental science and engineering from the National University of Singapore and her postdoctoral training in University of Illinois at Urbana-Champaign. Her goal research is to continue to push for the reuse of high-quality treated wastewater in water-scarce countries like Saudi Arabia and in a global environment. Dr. Hong is the recipient of 2019 James Morgan Environmental Science and Technology Early Career Award and the named finalist for the Lenten Prize 2023, awarded by the Lenten Foundation and the Young Academy of Norway. Her work has been highlighted by various media outlets like The Economist, Wired, and Arab News. And since September 2023, she serves as an associate editor for Environmental Science and Technology. Thank you so much for accepting our invitation, Professor, and now the floor is yours.
Thank you, Claudia. Thank you. I hope everyone can hear me. And thanks for taking time to attend the seminar today, and thank you for the invitation. So to present one of my pet topic, which is really trying to address water scarcity by looking at how we can use the water resources in a more sustainable way. And later towards the seminar, we will find that I'm more gearing towards one particular type of water resource, which of course I will not let you know at this moment what it is, but you will hear from it towards the later end of the seminar. So it's very important to really try to address how we want to use water in a more sustainable way, because we are increasingly faced by various challenges that is driven by the rapid population growth. And with rapid population growth, we are of course seeing an increase in the demand for the food production, as well as energy production to sustain all the human activities and the GDP of the different countries. And then with all of these, of course, further exacerbated by climate change, we are seeing, for instance, land degradation, soil erosion, and the drive towards mass afforestation effort to reverse the outcomes of those soil degradation outcomes. And all of these activities that I just mentioned just now actually requires a lot of water. And that's something that I want to further illustrate point by point what all of these challenges would mean in terms of how it imposes in terms of water demand. So the first challenge, of course, as I mentioned just now, is about the rapid population growth globally. So we see a very flat population growth for almost a few million years until about 1800, where the global population first hit about 1 billion. And since then, just within a short 220 years, our population growth has increased from 1 billion to the current 8 billion, and it is expected to further increase to 10 billion by 2050. So, of course, this means that we need to find out ways how we can host all of these 10 billion population, because the land mass on Earth is not increasing. In fact, this is decreasing because of the sea level rises, and we are having countries like Maldives or so on that is going to be lost due to the increase in the sea level rises. So one natural inevitable trend that is going to happen in the near future is that we're going to see more and more urban cities growing and sprawling up, because that's the only way that can host more people over a larger density in a very small population area. And this is where we will see, for instance, the blue circles that are where all the major urban cities are going to be. And of course, there are advantages in having them in urban populations, because that means more effective allocation of resources, distribution and transportation of resources, and so on and so forth. And in Saudi Arabia, where we are right now, the current population is about 33 million. It is expected to increase to about 40 million by 2050. And we know that the current usage rate, if we were to estimate on the more conservative side, is about 270 liters of water per person per day. So with this increase in the population growth expected from Saudi alone only, it will mean that we need an increase in about 2 million cubic meters of water per day just to meet the municipalities' demand. For instance, drinking water, bathing, showering, and laundry that is required by the increase in the population growth within Saudi Arabia. And that's, again, just as a reminder, within only Saudi Arabia. Globally, we're going to see an increase in the water demand as population growth increases as well. So this is the first demand in terms of our water usage from the global population growth. The second, of course, not forgetting, is about the fresh water that is needed to produce food. And we know actually municipalities that I mentioned just now, that 2 million cubic meters forecasted demand increase is nothing compared to the fresh water that is needed for agriculture. Because if you take a look at these numbers over here, this is the percentage of freshwater global supplies that are needed for agriculture. And of course, we see a pretty wide range here, depending on which continent we are talking about. Europe, only 20%. And then as we move to Africa or South Asia and Asia, we are seeing a high range of about 80 to 90% of our fresh water that is needed for agriculture. So in fact, if we were to average out all these sums globally, about 70% of our fresh water is needed to produce food. And this is indeed creating such a huge environmental impact that Dr. Jonathan Foley, who is the executive director of Project Drawdown, and he visited us he presented virtually at KAUST during the Winter Enrichment Program in 2022, that he said in an interview in May 2014 in the National Geographic magazine, that he says, when we think about threats to the environment, we tend to picture cars and smokestacks, but not our dinner. The truth is that our need for food poses one of the biggest dangers to the planet. And that is really true, because if you look at the statistics, even though we drink about 2 to 4 liters of water per day, we actually consume about 2,000 to 5,000 liters of water in the form of the food that we are eating in our 3 meals per day. So just to produce 1 apple will require about 70 liters of water. To produce 150 grams of steak, you will require about 2,025 liters of water. So that's a huge water demand as a result of our need for food. And that's something that we really need to think about, because again, with the population increase, just using Saudi Arabia as an example, we will need an additional 35 million cubic meters of water to produce the food in order to meet that increase in the demand as a result of population growth. And then, of course, the next sector that is going to require water is the energy. And we need energy. Everything that we are doing now is sustained by energy. And if we look into the business as usual case, where we are mining for the non-renewable fossil fuels, that is basically also a very water intensive activity. In Saudi Arabia, to mine 1 barrel of oil will require about 10 barrels of water. And that's already a very fertile mining activity. In other places where the oil is harder to excavate, you will need even more barrels of water in order to mine for it. So with 1 barrel of oil, you need 10 barrels of water. And of course, that water will get converted into wastewater. And that wastewater will also have to be dealt with accordingly as well. So when we talk about mining for oil, it's not just the oil, it's also the water that we need to talk about. So in fact, sometimes you can refer to the oil industry as a wastewater generating industry as well, because they are always tied hand in hand together. So then this is the business as usual case model when we are talking about fossil fuel. What about if we say now that we are transiting into renewable energies? How does it fare in terms of water demand? And that's basically a comparison between crude oil with the different types of renewable energy. You will see that from this graph, for instance, solar electricity, natural gas, uranium, and coal, which are the cleaner renewable energies, they seem to fare better in terms of our water footprint. In terms of their water footprint, is way much lower compared to that of the crude oil. So of course, that's good news, because we are now slowly transiting into renewable energy. But bear in mind that it's not a zero. So there's still a water footprint that is required from all this renewable energy production as well. of course, is lower. But what you would also see here is that we are missing on other forms of renewable energy, for instance, those related to biomass. And so if we talk about renewable energy, biomass is way non-competitive in terms of the water footprint. So just using the table here, you'll see that if it's biomass, depending again on the geographical location, it can sometimes range up to 143 cubic meters per gigajoules of the water footprint, which is way much higher than that required by the crude oil. So biomass as a form of renewable energy is not competitive, be it in terms of water and also be it in terms of the land that is required to grow the biomass. Because in order to grow the biomass, usually what happens is that you need to clear a large area of land for monoculture, and that's of course not good for ecosystem and diversity, and that can also result in degradation, landscape degradation and soil erosion and so on. So here I wanted to highlight that when we talk about energy, we require water. And so again, coming back to the previous when we already require 37 million cubic meters additional water to support the food production and the growth of the population. This is another additional amount of water that is needed in order to provide the energy that is required to support the population. And of course, depending on whether it's renewable energy or the non-renewable energy, the water demand will adjust accordingly as well. And then if we look into biomass, that is something that perhaps will not be very competitive if we were to consider in terms of the water footprint. And then of course, the other challenge is that now with all this awareness on sustainability and climate change, there has been massive push to reinstall degraded landscapes through perhaps massive afforestation efforts. So I guess you guys already are fully aware that Saudi Green Initiatives was released a few years ago, where they listed out very ambitious plans to plant 10 billion trees in Saudi Arabia, 50 billion trees in the Middle East. But of course, the elephant in the room is where's the water going to come from? Because to plant the trees is not just about planting trees, it's also about determining where the water is coming from, especially if those trees are to be planted in very remote areas, in desert areas and so on. There's a huge energy cost to get the water, to get the water and also to transport the water to reach where the trees are. So these are obviously things that has to be considered if we really want some initiative to be sustainable. All of these aspects have to be fully considered, which really motivated us and my colleagues about last year that we wrote a perspective to urge people to really consider how to move forward with some of the initiatives goals and consider perhaps moving some of the green initiatives to the urban landscape where you have easier access to water supplies so that we can then use them in a more sustainable way. And this perspective was published in Nature Water. So if you're interested, you can take a look into it. And our main goal for this is really to create awareness in the sense that initiatives like these are coming from a good perspective, but perhaps we need to consider from a more well-rounded aspect if we want to consider the overall sustainability of the goals. So coming back again to Saudi Arabia and the use of water in the urban cities, we know currently from our statistics that in Saudi Arabia alone, we require about 3.4 billion cubic meters of water per year just to sustain it within the urban population. And out of these, the four major sources of water is desalinated water, groundwater, and then the rainfall and the wastewater. Okay, so these are the four sources of water that is currently used. Think about it as the four water taps that Saudi Arabia is tapping into, and the numbers that are related to each one of them. So with this in mind, maybe can I invite you to go to the menti.com if you can, using the code of this. And I would like to ask, which one do you think in your perspective is the most sustainable water source? So majority of you perhaps already know what I'm working on. So you chose wastewater, that's good. So you don't need to be further convinced of my later pitch anymore. But there are still some of you who chose surface water, seawater and groundwater. So hopefully I can convince you, the 15 of you, why perhaps that is not the most sustainable water resource. The rest doesn't need further convincing. You can leave the seminar now. So in terms of the first desalinated water, so the current technology to get seawater converted into fresh water is by means of reverse osmosis. Okay, so that's the main technology. Of course, there are other technologies as well, but majority of the desalination treatment plants right now, they are mainly using reverse osmosis, otherwise termed as RO over here. So the process is usually they will have to construct a pipeline into the sea, open sea, usually a few kilometers into the sea. And then that's where the intake happens. And then before they can go directly to the reverse osmosis system, they will have to do a pre-treatment. That pre-treatment usually involves the addition of chemicals, or it can also involve the use of, let's say, ultrafiltration membranes or some other dual media filtration systems, so as to remove as much as they can microorganisms or other stuff that will rapidly degrade the integrity of the membrane, of the reverse osmosis membrane. So once the pre-treatment is done, the reverse osmosis membrane will then try to will then convert the seawater into fresh water. So for those who are not familiar, basically it uses a reverse osmosis membrane in which the theoretical pore size of the membrane is so small that only water molecules can pass through the membrane. But of course, that is theoretical. There will still be some anions like boron, bromide that can pass through the reverse osmosis membrane as well. So after that, the RO will then go through post-treatment, which perhaps will be including blending of palatable salts to make the water more palatable, because if they don't do that, the water by itself is not really drinkable. It doesn't taste nice. They can also involve the addition of disinfectants to make sure that during the distribution pipeline, there will be no microbial activity existing. And then you can have your fresh water from the seawater. And that's the current technology that we are heavily reliant on. And in fact, this technology is perhaps one of the most important technology for Saudi Arabia, because if it's not because of this technology, it will never be able to sustain the 33 million population growth that's happening right now in Saudi Arabia. So, but we also have to recognize that even though it's a very important technology, it basically performs miraculous outcome, that it is a very energy intensive process. Okay, so here is a graph from a scientific paper that shows the specific energy outcome on the y-axis in terms of kilowatt per cubic meters of seawater converted into fresh water over the commissioning year. So let's say starting from 1990s, where the reverse osmosis membrane started to really become more prevalent, all the way to 2020 on the x-axis. You can see from the different data points that are collected from the full-scale, pilot-scale desalination plants that the specific energy consumption of seawater reverse osmosis is about 4 to 5 kilowatt-hour per cubic meters. So to put that into context, an LED light bulb is about 10 watts per 10 watts. So that means about 400 to 500 light bulbs have to be lit up every time you convert per cubic meters of seawater to fresh water. So that's quite a lot of energy that's required to convert the seawater to fresh water. And of course, technology is advancing. And in fact, Saudi Arabia, which is the global producer, top producer of desalinated water, has been really advancing a lot in terms of the desalination performance. So in 2021, they actually achieved a Guinness World Record where they managed to bring down the specific energy cost in one particular plant from the usual about 4 to 5 kilowatt per cubic meters to about 2.3 kilowatt hour per cubic meters. So that is actually it's a Guinness World Record. It doesn't mean that it can be easily translatable to every individual desalination plant, but at least they demonstrated that in this particular plant, through some modifications of the technology and so on, they are able to bring down significantly half the energy cost of desalination process. So this is not an easy feat, but it's perhaps doable. So even with that in mind, you will still need about 230 light bulbs to be lit up in order to convert 1 cubic meters of seawater into fresh water. So that's the energy part. in terms of the sustainability, which perhaps is not very sustainable for seawater. The other aspect of desalination process, the so-called the disadvantage of it is that it also produces a lot of brine. And this brine can be a problem depending on what how you think about it, because here, for instance, in this article that was highlighted in Bloomberg, it says that Saudi Arabia, which is the world's global top producer of desalinated water, is also producing a lot of waste in the form of brine discharge. It makes about 893 million barrels of waste in the form of brine per day. And currently, how is the brine solved? How is the brine handled? Any guesses? How is the brine handled? Yes? Yes, so it's usually currently only like pumped out into the sea and then diluted by the sea. That's kind of the usual way that they deal with it. Of course, there is also a push to try to extract valuable minerals as much as they can before they put it out into the sea. And there are, of course, other regulations that perhaps will be coming out very soon to deal with the brine problem as well. But currently, as per the current status, is basically just diluted by the sea. So of course, there's also contradictory research to say if this is going to be an ecological problem or not. Some people say that there is, especially at the point where all the waste accumulates. And some people also have research that suggests that it perhaps is not a big deal or problem. But in the face of contradictory outcome as to whether it has a detrimental impact on ecosystem or not, I think the usual way is to err on the precautionary principle, which is to treat them as something that is possibly toxic and has to be looked into. So in that case, desalination in terms of both energy and ecosystem perhaps is not very sustainable. But of course, we still need to rely on desalination. There's no escape from that. We need desalination to get the water needed in hyper-arid environment. Then what about the other one that some of you chose, which is in terms of surface water? So here I have the title as surface water double whammy effect. I'm not sure if that's a very good title, but let me explain why I say it's a double whammy effect. First of all, here we know that in Saudi Arabia, rainfall doesn't come very easily. If we are lucky, we get a few rainfall in December, maybe, and then there's leakage in the KAUST ceilings, which is what happened last year. And it sometimes happens, sometimes it doesn't happen. For instance, I've been here for 12 years, and the first few years, I hardly see any rainfall. It's only recently that I start to see a little bit more rainfall. And it's likewise the same case. If rainfall happens, it's highly variable. So here we have a data of rainfall events in Riyadh, Tabuk, and Abha. And you can see that, for instance, in Tabuk, the rainfall level is way much lower than that in Riyadh and Abha. And then if you look at the standard deviation bar, you can also see from the standard deviation bar that is a highly variable event. So within the same location, you can have a very highly variable event as well. So what this data suggests to us is that rainfall in Saudi Arabia shows a high spatial and temporal variability. So it's very hard to predict when exactly the rainfall is going to come. So if you have something that's so unpredictable, how can you rely on it as a consistent source of water? Unless you can store it, which is what is needed. So if you can store it in surface reservoir, that would be good, because Saudi Arabia has a lot of land. It doesn't mind having a surface reservoir to store as much water as they can. But the main challenge is that evaporation rates in Saudi Arabia is extremely high as well. So if you see, for instance, here, the evaporation rates in places like Riyadh, where we are expecting rainfall, it is shown as a red color over here, suggesting that the evaporation rates are very high. So whatever water that you store, perhaps will be evaporated off, which leads to water losses over time. And that rainfall event will not come again very easily as well. So this, again, makes things very difficult to rely on surface water as a reliable source of water. And this brings us again to wastewater as perhaps one of the most resilient, climate resilient and sustainable source of water. And that is because even with rapid population growth, we are going to expect more wastewater to be generated too, right? So if you have rapid population growth, there are more people, they're going to generate more wastewater. So the trick is to capture all those wastewater that is generated by the people, treats them, purify them, clean them, and then reuse them effectively. So if we can do that, that will ensure a very circular water loop that can sustain the use of this water for a pretty good period of time. And that's primarily the main goal of some of our research, which is what we want to tap into the potential of the wastewater. But unfortunately, in Saudi Arabia, we still have very low capture rates of wastewater. Currently, only about, let's say, 60 to 70% of the wastewater is fully captured and purified and clean. And then out of those purified wastewater, only current reuse rates hover around the range of 30%. So we are not maximizing the full potential of wastewater at this current moment. And of course, those are things that we want to work towards too, either in terms of outreach and in terms of technological advancements. And one of the main things that we want to really convince people when we talk about wastewater is that when you think about wastewater, you will think about, it's so yucky, there's so much contaminants, bacteria, viruses, chemicals, protozoa, and all this is not safe for reuse. And that's really what we are trying to change people's perspective in terms of wastewater as well. And of course, that is the challenge, but there are already technology to help remove as much of those contaminants as we can. And of course, I'm not talking about 100% removal because there's no such technology that can remove everything. But we are talking about removing of those contaminants to a level that is low enough to ensure the risk is within acceptable limits. And that's really the goal of most of the decisions and policies and technology developments as well. So if we look at the current existing wastewater treatment facilities, perhaps the one that has the most potential to achieve that in terms of purifying the contaminants and minimizing the risk as much as we can is the use of membrane bioreactor. Okay? And in a typical aerobic membrane bioreactor, which is what we have here in KAUST. So the KAUST wastewater treatment plant is operating using the aerobic membrane bioreactor. So for those who are not familiar, how does it work? So you have the wastewater goes through the screen grid chamber. It's basically a very large mesh that tries to remove the big bulky materials. Sometimes you have a primary clarifier in between, sometimes you don't have, but mainly this is just to do a preliminary physical separation process to remove some of the solids that can settle down within a few hours. And then the water portion will go into the main system, which is the conventional activated sludge process. So this is where the majority of the activity happens, where we make use of aerobic microorganisms to degrade the organic carbon and to remove some of the nutrients like ammonium and phosphate that are present in the wastewater. So this is where the main activities happen in the wastewater treatment plant. And then the coupling of a membrane filtration will help to provide a size exclusion. So you remove some of the particles and the microorganisms because of that size exclusion imposed by the membrane filtration process. So after that, the clean water will go to the last stage, which is the chemical disinfection process. So this is the usual, or perhaps one of the current way of cleaning the wastewater that perhaps does the best in terms of removing the majority of the contaminants to a level that is safe enough for reuse. And of course, as part of Vision 2030, the plan is to upgrade a lot of the existing wastewater treatment plants in Saudi Arabia, but not all of the plants are currently having the membrane filtration. Most of the plants are perhaps using this without the membrane filtration, but the addition of a sand filtration after the activated sludge columns. But one can argue perhaps that may also be less effective than that of a membrane bioreactor process. So now that you are familiar, kind of, with the existing wastewater treatment plants, I have a second question for you. So if you were to define what a sustainable wastewater treatment system is, which criteria do you think is the most important to achieve sustainability? Is it in terms of energy costs? Is it in terms of low solid waste production? Or is it in terms of the ability to recover resource? Which one do you think is the most important criteria for you in terms of defining sustainable solutions? So most of you either chose low energy costs or the ability to recover resource, and lower number of you chose low waste production. But I would argue that all three perhaps are very important. Of course, it depends on how you look into it. And I will maybe my case in point is that I will try to so-called convince you why the current aerobic wastewater treatment process may not align with all three of them in terms of energy costs, in terms of the ability to reduce the waste, and in terms of recovering of the resources. So the first case in point is that the energy demand of aerobic processes is actually quite high. So it's mainly because of the need for aeration, because aerobic microorganisms require dissolved oxygen, so they will require you to aerate that water. And that aeration requires energy costs, because if you need to provide dissolved oxygen into the water, you will need to keep on using mechanical pumps to aerate the water, and that requires energy. And then after that, as you pump the water from one stage to another, that also requires energy. And also with the solid waste that is produced, you will also require additional processing and handling of the solid waste, which requires energy. So here again, another paper that was published in 2011, they looked into several of the full-scale and pilot-scale wastewater treatment plants that uses aerobic-based technology. And they found that depending on which plants they're looking at, the specific energy demand, again, demonstrated in kilowatt hour per cubic meters of wastewater that is purified, would range from about 0.5 to sometimes about 2 kilowatt hour per cubic meters. And that's just the aeration costs alone. If you were to add the membrane, because I want better water quality, if you were to add a membrane, you will easily add about 0.5 kilowatt hour per cubic meters additional. So this means that depending on whether you have a membrane or not a membrane, and of course you want a membrane because you want to reuse the water in high effluent quality, that will incur about 2 kilowatt hour per cubic meters to purify the wastewater. And remember, just now I told you desalination with the Guinness World Record is 2.3 kilowatt hour per cubic meters. So this is not a very competitive specific energy cost that we are talking about. And this energy demand is almost currently on par with desalination if desalination energy cost continues to drop. So then if that's the case, why would we want to use wastewater? I would rather just use desalinated water, right? So obviously this is not competitive, and this is something that needs to be looked into. And in addition to that, of course, the energy cost is not competitive. We can also look at the global warming potential of aerobic membrane bioreactor. Because if we look at each of these steps, this is gotten from a US EPA document. And if we use each of these steps and then try to map out the CO2 that's produced as a result of purifying the wastewater, and then average out by the wastewater that's purified, an aerobic wastewater treatment process with a membrane would produce about 0.6 kg equivalent of CO2 per cubic meters of wastewater that's cleaned. So let's just put it into a context of, let's say again, the KAUST wastewater treatment plant. So KAUST wastewater treatment plants purifies about 4,000 cubic meters of wastewater per day. So this means that each day we are generating from that plant alone 2,400 kg of CO2. Okay, and that is going to contribute to the global warming potential. So next, in terms of energy, it's not very sustainable. So what about the solid waste, which less of you chose it, but I will also argue this is something that we need to consider as well, because the current aerobic-based wastewater treatment process produces a lot of solid waste. And that's as a result, and that's because those microorganisms that I said is in charge of removing the organic carbon and nutrients, they grow at a very crazy rate. So the more, and they need to grow because they are related to the removal of the organic carbon and nutrients. And when they grow, they produce a lot of solid waste, and you need to clean, and the plant's utilities will have to remove those solid waste on a regular basis, sometimes even on a daily basis. So here is the data that we got from the KAUST wastewater treatment plants. And we can see that in terms of liters of sludge produced, it's usually about the range of 0.5 to 0.8. So this is the wet solid. And if we remove the water mass within this waste, we will still have about 0.2 kg of solid waste that needs to be disposed. So again, put that into context. the KAUST wastewater treatment plant treats about 4,000 cubic meters of wastewater per day. So in turn, it generates about 800 kg of solid waste per day, if this is based on the data that I've shown here. So every day it has to get rid of 800 kg of solid waste. And that means that you are going to add to the costs of the plant operation. Because if you look at the costs, a typical cost of operating a wastewater treatment plant, of course, the main cost comes from the energy. And I said that the energy is mainly because of the aeration. So it sometimes even takes about 41% of the energy cost. And then the third biggest cost would be in terms of handling of the solid waste. So the more solid waste that they generate, the more cost is going to become to deal with those wastes. So again, this is not sustainable in both costs and in both energy perspective. And of course, those solid waste needs to be properly treated, because this is where all the nasty stuff, the chemicals, the microorganisms accumulate. So you can't just throw them somewhere and then think that it will not have any problem. You will need to properly treat them as well. So those are also potential ecosystem problems if you don't deal with those sludge properly. And the last point in terms of recovering of resources, which majority of you chose as well, is not sustainable, because even though you define that as a very important sustainability criteria, I would argue that the current aerobic processes is not very sustainable in that sense. And the case in point is that it removes ammonium and nitrates from the wastewater. And that is required because the current regulations stipulate that any final effluent needs to meet, for instance, 5 milligrams per liters of ammonium and 10 milligrams per liters of nitrate. So it's based on regulations. So they remove it, but the regulations is devised because majority of the wastewater treatment plants is based on aerobic processes. So usual aerobic processes does very well in removing the ammonium. So here is again the KAUST wastewater treatment plant, where the influence has very high ammonium concentration, so the ones on top. And then as it goes through the wastewater treatment process, almost all of the ammonium is now no longer detectable or present in very low abundance. Majority of them are now converted or utilized by the organisms to convert it into nitrate. So the final predominant form of N is in the form of nitrate. So here you can see that the nitrates does meet the stipulated requirements, less than 10 mg per liters. And that is because our KAUST wastewater treatment plant is very well operated and is on par with the regulations. But it basically removes a lot of the ammonium. And why is that a waste? Because I can argue that those ammonium are actually very important for food production. Because the reason why food production is very important because why we can still able to feed the current 8 billion is mainly because of the green revolution. And the green revolution happens because of the intensive use of chemical fertilizers. So the farmers actually over fertilize the land, and they use a lot of chemical fertilizers, such that it of course leads into seepage of nitrogen into the natural environment and so on and so forth, which is why you always read about people saying, oh, we need to, let's say, for instance, in this article, that they say we need to reduce our nitrogen use to sustain our human and planetary health. But I would argue that it's not about the nitrogen. It's not about the nitrogen alone. It's about our overuse of chemical fertilizers. So instead of trying to remove the ammonium and nitrate from the wastewater, which is what it's currently doing, perhaps we can reduce the chemical fertilizers and make use of the natural ammonium and the nitrate that are present in the treated wastewater in a more sustainable and well-practiced way. That would be a much better outcome and a much better option. And in fact, they are still, of course, continuing as business as usual, still relying on chemical fertilizers. Chemical fertilizer costs have skyrocketed over the years. And the world is so desperate for those fertilizers that they are now looking into manure, which is again crazy because this is untreated manure that we are talking about. So perhaps one really needs to think about a change in our thought process and our paradigm, that regulations should not be fixed, but perhaps should be flexible enough to meet into the local context. So perhaps wastewater should be purified in a way that ammonium and nitrate can be retained so that we can then use them more effectively and then reduce the chemical fertilizer usage. And the last problem with the current wastewater treatment facilities is that the current design of our wastewater treatment systems is mainly developed based on a centralized wastewater treatment process. And what do I mean by centralized wastewater treatment process? It means that they will usually build a very, very large wastewater treatment plant in the middle of somewhere or nowhere. And then they will try to tap all the wastewater from the cities, from the municipalities, and then have them transport over long distances to reach those centralized wastewater treatment plants. And what is the disadvantage of that? There are many disadvantages of that. Of course, there are advantages. They don't do that for no reason. The advantage of that is to make use of economies of scale, because when you need to treat large volume of water, you incur the benefits of economies of scale. But there are various disadvantages associated with that, because first is that you will require long transportation distances. And with long transportation distances, it means that you need more energy to pump from one place to another. Okay, and then during the transportation process itself, you can incur water loss, maybe because of pipeline leakage, maybe because of other uncontrolled factors. So water losses due to transportation can be about 20%. And if you have wastewater that is lost, you also lost into environment, that can also be a detrimental outcome. And then when you treat the wastewater and you want to reuse it, you have to pump it back from the wastewater treatment plant to wherever you want to reuse it. And at that point, it's going to be harder to control the water quality because the distribution system network may be very long. So it's going to be harder to control the water quality, and it will be very hard to ensure that your wastewater is used very safely at the point of reuse. And then, of course, small populations are not efficiently served by centralized wastewater treatment plants, and then they have to rely on septic tanks, like what we are seeing in Saudi Arabia right now. And then so on the other spectrum of centralization is decentralization. So decentralization is smaller wastewater treatment plants serving a smaller municipalities. You can have a higher number of those wastewater treatment plants. So the benefit of it is then you can basically address all the disadvantages of centralization wastewater treatment plant, because you can have shorter distribution network. You would transport them over shorter distances. And then because you have more of these wastewater treatment plants, there's a certain level of redundancy and resilience that is built. Because if you have one wastewater treatment plant, centralized wastewater treatment plant, that's hit by climate change or extreme weather conditions, and it has to be shut down, then you have zero wastewater treatment facilities. On the other end, if you have a lot of redundancy, then you can also have resiliency, because the probability of having all of them hit by natural extreme conditions is very, very low. It's slightly lower than that of having one hit by natural extreme conditions. So there's a certain redundancy in having certain resilience in having redundancy in systems that is imposed by decentralized wastewater treatment facilities. So with that in mind, now that I have made my case to say that our existing wastewater treatment plants are very, very needed if we want to push for wastewater reuse, but perhaps not very sustainable, I think what we really need to think about is whether we can reimagine our wastewater treatment plants and make them more sustainable. And so my preferred criteria would be perhaps to have a decentralized system, because you can have lower transport costs, better control of water quality, preferably one that moves away from aeration systems so that you can reduce aeration costs, odor and gas emissions, and to reduce large production, retain valuable nutrients, and perhaps also diminish the reliance on chemical fertilizers, chemical disinfection process. So these are my preferred criteria. So for that, we have been working, our group has been working a lot on developing anaerobic membrane bioreactor with non-chlorine based disinfection process, because we want to tap into as much of those preferred criteria as we can. And we believe anaerobic membrane bioreactor has the maximum potential to really achieve majority of those criteria. So for those who are not familiar with anaerobic membrane bioreactor, it basically utilizes a totally different set of microorganisms, so one that does not require oxygen. So instead of what I've just described to you that relies a lot on aeration, anaerobic membrane bioreactor uses anaerobic microorganisms that do not survive well in the presence of oxygen. So in the absence of oxygen, certain populations will convert the organic carbon into methane. And that methane, yes, is a greenhouse gas, but no, it can also be minimized by capturing them and then converting them into energy source. does not require aeration, so there will be an improved energy landscape because it totally eliminates the need for aeration. And anaerobic microorganisms grow a little bit slower, so there's less solid waste that's produced. And the good thing also is that these anaerobic microorganisms do not touch the ammonia and phosphate. So the final effluent basically has the ammonia and phosphate, which makes it particularly attractive to be used for food production or for landscaping irrigation. And then, of course, if we can couple it with membrane filtration, we can ensure a much better water quality. So I prepared this slide last year, so it says 11-year journey, but it's basically 12-year journey now. I have not updated this slide. But over the past 12 years, we have been working from small lab scale 2 liters bioreactors to really looking at fundamental questions, how to solve fouling, how to design reactor configurations, and so on and so forth, and then started to scale up and demonstrate business and technical feasibility. We scale from 2 liters to 35 liters of reactors, and then we have been operating a demo scale of 50,000 liters wastewater treatment plants in Jeddah, in the industrial city in Jeddah, from 2022 until now. So I'll play a short.
From what you see over here, we are right now at the wastewater treatment plants. We are here with our anaerobic membrane bioreactor prototype to demonstrate the next generation of treating and cleaning our wastewater. What we hope to do is to have a decentralized way of treating wastewater and harvesting the energy that's present in the wastewater and converting them into methane energy, which can then be converted into electrical energy. And by doing so, we can make use of the energy that is contained within the wastewater to finance the entire operation of cleaning our wastewater with the end product of a high quality reclaimed water that can be used for other non-portable reuse purposes, such as for food production, as well as to enhance livability by growing green landscapes in the urban environment. The wastewater from Modon is coming through the pipes that enters into the equalization tank. The equalization tank serves to equilibrate the flow rate so that it can go into our anaerobic membrane bioreactor, which is the taller structure that you see at the background. Inside the anaerobic membrane bioreactor, we have anaerobic microorganisms that are tasked to convert the organic carbon into methane. So the supernatant then goes into the membrane filtration tank, and this membrane filtration serves as an additional physical removal process to remove the particulates that may be present in the wastewater to get better effluent quality. This effluent then goes into a disinfection process, which is the UV reactor that you see at the back. So together with hydrogen peroxide as a chemical disinfectant, we have a UV hydrogen peroxide based disinfection to serve as a final disinfecting of the clean wastewater. The clean wastewater then goes into a final polishing step, which is through the activated carbon column over here. And by then, we expect that the wastewater will be of very high quality that can be used for other purposes, such as for landscaping irrigation, or maybe even for food production.
So over the past 2.5 years, we have been operating the wastewater treatment plants in Modon, and it's still continuing to happen. It's still in operation. And we have been collecting our data from the wastewater treatment plants to really try to demonstrate a business case and also to try to convince people that there is an alternative technology out there that is offering at the full, not full, but pilot scale wastewater treatment plant that is operating pretty well. So here we see the COD removal. For those who are not familiar, what COD is basically related to organic carbon removal. And our plant has been operating over the past 2.5 years, achieving about 90% removal of COD over that period. Of course, there's always ups and downs because, as I said, this is happening in an industrial city. So we can't really control what the industry companies are throwing into the wastewater. So sometimes the pH can be in acidic range, sometimes it can be an alkaline range, sometimes it can be very high COD, sometimes it can be very low COD. But this, in spite of all these variations, highly variable conditions, our wastewater treatment plants continues to stay very robust and stable in terms of removing the COD. And then that COD gets converted into energy. So this is the average energy production that is because of the methane production. So we have about 1.5 kilowatt hour per cubic meters of energy that's produced from the waste purification alone. And of course, this is not something that can fully sustain the entire wastewater treatment plant, but it's at least a demonstration of the fact that we can indeed recover energy from the wastewater. And because, as I said, it is not enough to sustain the energy requirements of the entire wastewater treatment plant, our plant has also been equipped with solar panels to try to tap into the renewable energy, the solar energy. And because of the panel production and the panel that we install, we are able to produce about 410 kilowatt hour of the solar energy that is stored in battery units that are located on site. And with this and the methane energy that's harvested, we have demonstrated that in theory, we are able to run the entire wastewater treatment plant without connecting to any landline electricity. So this makes it particularly attractive to work as a decentralized wastewater treatment sanitation system in off-grid communities that perhaps do not have easy access to electricity. So, and then in terms of the resource recovery, again, I'm trying to demonstrate why we think our technology is able to fit all the criteria of sustainability. We here have a comparison of our aerobic MBR versus our anaerobic MBR. So the aerobic MBR is what I've shown you just now. The solid waste production is very minimal compared to aerobic MBR. So it means what this means is that you don't need to dispose of the solid waste on a very regular basis. So you can accumulate them over a certain period of time before you incur costs to deal with the solid waste. So you minimize the detrimental impact of the solid waste. And now, of course, with all of this, it also means that the global warming potential of the anaerobic membrane bioreactor, because of the elimination of the aeration costs, because of the need to handle lower volume of sludge, the CO2 production of the anaerobic membrane bioreactor is anticipated to be half of that of an aerobic membrane bioreactor. So it's more competitive in terms of global warming potential as well. And then what about the effluent quality? Because my whole set of seminar is that we want to make use of the effluent quality. And we've also, of course, really focused on the effluent quality because this is really our core business as well. So we've been looking at the removal of E. coli by our anaerobic membrane bioreactor in Jeddah wastewater treatment plants. And we found that just by the anaerobic membrane bioreactor, we can achieve about 5 log removal of the E. coli. And when we mean 5 log removal, it means 99.999% removal of the E. coli from the untreated wastewater to our effluents after the anaerobic membrane bioreactor process. So of course, this is still not good enough because when we look at cultivating the E. coli, we found about 60 CFU per 100 ml. And if you are familiar with the regulations for reuse, the regulations for reuse requires about 2.2 CFU of E. coli per 100 ml. So currently with the 60, after only the anaerobic MBR, it does not meet the regulations for reusing for crop production. So that's why the need for the disinfection is very important. And we show that after the UV disinfection, we basically don't detect any more E. coli. So in that case, it will meet the regulation. So there's an additional 2 log removal as a result of the disinfection process itself, which is why we really wanted to demonstrate the entire wastewater treatment plant, not just the anaerobic MBR, but also the disinfection process also. And then after that, demonstrating in terms of the reuse. So in terms of reuse, again, I here show that the anaerobic process do not remove the ammonium. So we have the ammonium in the influent that is shown by the blue dots, and in the effluent, we still have the ammonium. So the ammonium gets retained and the nitrate level is very low because it is an anaerobic process. So the nitrate is not expected to be predominant. So this is expected, but majority of the N species in the final treated effluent is in the form of ammonium, which would be beneficial for food production and landscaping irrigation. So in conclusion, I think I want to convince you through this seminar that when we look into the water demands in the urban city, we need to take into account of all the different challenges that are faced as a result of population growth, food production, energy production, and the landscape restoration efforts. We need to understand what the different sources of water are and to understand there are pros and cons Of course, there is a need to really diversify our water portfolio. I'm not saying only rely on wastewater, because if you do everything with wastewater, there's just not enough wastewater to go about. Because, for instance, the Saudi Green initiatives nowadays, they keep saying all the plants will be grown using treated wastewater, but there's not enough wastewater to really grow that 10 billion trees. So we really need to diversify our water portfolio by minimizing the cons and maximizing the pros. And we also need to understand that there are technologies out there to convert seawater to fresh water and purify wastewater to clean water, but they can be improved in terms of their overall sustainability. And if that's the case, we really need to perhaps change our current paradigm in how we want to design the future wastewater treatment plants. We need to consider efficiency. Maybe we need to move away from centralization to decentralization. We need to enhance the sustainability. Maybe we need to move from aerobic to anaerobic-based wastewater treatment plants. And if that's the case, we have demonstrated that anaerobic membrane bioreactor-based wastewater treatment technology is feasible, but perhaps requires more engineering solutions, more engineering work to be done to really scale them up. And because we've only operated it using only 50,000 liters, which is 50 cubic meters. So if we want to further scale it up, we will need to work more with engineering companies to further scale it up. But it is possible. And I think this is something that we really need to consider in the future as well. And so with this, thank you very much. And thank you to my team for the excellent work. Thank you.